So we've seen how to use integrals to provide lower bounds for series. Now we're going to see how we can use them to give us upper bounds. Okay, so we're going to look at the example f of x equals 1 over x squared. And we're going to try to use it to understand the sum from n equals 1 to infinity of 1 over n squared. Okay, so this is the series that looks like 1 plus 1/4 plus 1/9 plus 1/16, and so on. Okay, so each time we square the index and take its reciprocal. Okay, so my claim is that if we look at the series starting at n equals 2, if we add from n equals 2 up to capital N, this is going to be less than the integral from 1 to n of 1 over x squared. Let's see what this means in action. So let's take capital N equal to 5. Okay, so let me draw in this region that we're going to be integrating to get my supposed upper bound. Okay, so I'm trying to compare this this blue shaded region with the sum 1/4 plus 1/9 plus 1/16 plus 1/25. And let's see how we can represent that in this picture. I'm going to erase the shading so that it's easier to see. Okay, so we're trying to use this as an upper bound. 1/4 is the value of f at 2. Okay, so a rectangle that has this area is going to be this right-hand estimate. So this is area 1/4. Okay. Similarly, 1/9 is the value of the function at 3. And so using this right-hand endpoint as the height of my rectangle, this shaded area has area 1/9. Okay, and then here we have area 1/16 if I use the right-hand endpoint. And finally, area 1/25 if I use the right-hand endpoint. We know that the integral is going to be bigger because we have that f is decreasing. So f at n plus 1 is less than the integral from n to n plus 1 of f of x dx. Okay, so then the idea is that our partial sum Sn, or S capital N, excuse me, is equal to 1 plus the sum from n equals 2 to capital N of 1 over n squared. So this is going to be the Riemann sum with width of 1 using the right endpoints. Okay. And this is less than or equal to 1 plus the integral from 1 to capital N of 1 over x squared dx. Okay, so we have this sort of oddity of not including the first term, just because we have a discontinuity at 0, so I don't want to consider that. That's why I've stripped off this first term. Okay. All right, we know that as capital N goes to infinity, we know that the improper integral converges. So we have 1 plus 1 to the infinity of 1 over x squared dx is finite. Okay. So Sn is some bounded increasing function. And so from our sequence section, when we said that bounding monotone sequences always converge, we know that the limit as n goes to infinity, as capital N goes to infinity of S capital N exists and is finite. Okay, so knowing that our function converged in the improper integral told us that our series converged. In this case, when we had a function that was positive, continuous, and decreasing. Let's see this in general. Note though that we haven't calculated what it's actually equal to. We've just figured out that the series converges.